Let us discuss nucleation. The complex subject of crystal nucleation and growth has been the focus of several specialists, investigators, and scientists. However, in practical terms, it is yet partly an art. The knowledge so far provides a reasonably good foundation for making intelligent guessing about new or unobservable crystal growth situations, but is far from being a foundation for making scientific predictions. In having some basic understanding of the theory of nucleation and crystallization, we shall consider mainly crystallization from the melt, while making some limited reference to crystallization from solution or vapor. Wherever some idea about nucleation, we shall consider crystallization of pure liquids. In this regard, supercooling is an essential requirement. If a liquid were not supercooled, slide number 6, the initiation of the transformation of an unstable to a more stable state is called nucleation. It may also be defined as spontaneous appearance of little order domain in the midst of randomness. Let us consider a familiar example of cooling of water with time. The ideal cooling curve appears to be as shown in figure 24.2. However, less ideal cooling curve of water is of the type as shown in figure 24.3. Let us perform a familiar experiment of making observations and recording temperature while a liquid is cooling. One would notice a pattern of the type shown in figure 24.4, which represents the cooling curve of a liquid. It may be noted that the temperature accurately at the instant when crystallization just starts spontaneously. One would find that the temperature at which nucleation just starts is always lower than the melting point. The temperature at which this happens is taken as nucleation temperature, abbreviated as NT. In this situation, one can say that the liquid has supercooled and is in a state of metastability. All liquids supercooled, and delta T, as shown in figure 24.4, is the supercooling at the nucleation temperature. Supercooling of water has also been represented by less ideal cooling curve for water in figure 24.3. Referring to figure 24.4, which represents cooling curve of a liquid, nucleation has occurred at the point capital A, and the process takes place between the points capital A and capital B, and also between the points capital B and capital C, is called crystal growth. The initiation of transformation from metastable to a more stable state takes place at the point capital A, and this process of transformation continues along the route capital A to capital B to capital C of the curve. Slide 7. Figure 24.4 shows the cooling curve of a liquid. Now we will talk about the types of nucleation. Nucleation is of two types: homogeneous nucleation and heterogeneous nucleation. If nucleation takes place in absolutely pure materials, it is called as homogeneous nucleation. Nucleation taking place as a result of foreign particles is called heterogeneous nucleation. Slide 9. Figure 24 point. The nutrient or the field material is placed in this part where it dissolves. A frame holding the seed crystal is placed in the upper portion called as crystallizing zone or growth zone. A perforated metal disc or baffle separates the two zones into two nearly isothermal regions and promotes the growth of crystals of uniform dimensions throughout the zone. The seed crystals are crystal plates of quartz cut along certain suitable crystallographic directions, namely X cut, Y cut, Z cut, etc., as shown in figure 29.3. In commercial plants, several seed plates are placed in racks so as to grow large number of crystals in a single run. The commercial plant is shown in a schematic diagram of figure 29.4. After the vessel is charged with solvent to the percent of fill desired, it is closed and placed in a furnace that gives the desired temperature and temperature differential. The moment temperature of the vessel reaches the operating conditions, the nutrient quartz starts dissolving and saturating the solution. Circulation results from convection currents, since the hotter zone is arranged to be at the lower part of the vessel. When the situation rises into the cold region of the vessel, that is the upper part, it can no longer hold all the dissolved material in solution and the excess gets deposited on the seed plate. The seed plate begins to grow in size. Replenishment is influenced by the baffle arrangement as it transports newly saturated solution away. This continuous cycle of solution and deposition permits the growth of large crystals. The rate of growth depends on temperature, pressure, the temperature difference, delta T, between the top and bottom of the autoclave and the amount of mineralizer present. The actual conditions used for the growth of quartz are to be compromised, in which various factors are balanced to provide the best possible material at a realistic production rate and cost basis. Figure 29.3 shows the model of a quartz crystal, showing the different directions of cutting to produce oscillator plates of different characteristics and also used as seed plates for growing synthetic quartz. Typical operating conditions for the growth of quartz are dissolving temperature 400 degrees centigrade, crystallizing temperature 360 degrees centigrade. Temperature difference delta T is maintained at 40 degrees centigrade. The degree of fill is around 80%. Aqueous alkaline solution 1 m of sodium carbonate or sodium hydroxide. baffle opening is kept at 5%, and the pressure is maintained approximately of the order of 30,000 pounds per square inch. Using these conditions, single crystals of quartz have been grown in the production vessels weighing several kilograms. Figure 29.4 is a schematic diagram of an autoclave which is used for commercial production of synthetic quartz. Let us talk about mineralizers. The materials that are grown by hydrothermal method have either negligible solubility in water or are slightly soluble in water. To increase their solubility, some substances are added. These substances are called mineralizers. The mineralizers usually used for this purpose include both alkaline as well as neutral substances. The alkaline substances are sodium hydroxide and sodium carbonate, whereas the substances which are more or less neutral include ammonium chloride, chemical formula NH4Cl, potassium chloride, chemical formula KCl, sodium chloride, NaCl, and so on. In the growth of certain crystals, acid solutions like hydrochloric acid, that's HCl, sulfuric acid H2SO4, and HI are also used. Generally, increasing the concentration of the mineralizer increases the solubility of the material being grown. For alkaline mineralizers, the solubility of the material being grown is proportional to the hydroxyl ion concentration, which is a function of the temperature and pressure. Some typical mineralizers under some specific conditions are given here in table 29.1. Now in table 29.1 we have 4 columns. One represents the crystal, the other mineralizer, the third the growth temperature in degree centigrade, and the fourth temperature difference, that is delta T degree centigrade. The first SiO2, that's quartz crystal, for which mineralizer is 1m NaOH. The growth temperature is maintained at 375 degrees centigrade, and the temperature difference, that is delta C, is 40 degrees centigrade. For the crystal of Al2O3, the mineralizer is 1mK2CO3. The growth temperature is 490 degrees centigrade, and the temperature difference is maintained at 50 degrees centigrade. PbTiO3, for which the mineralizer is 1mKf, growth temperature is 600 degrees centigrade, and the temperature difference is maintained at 35 degrees centigrade. For the crystal Fe3O4, the mineralizer used is 2m NaOH. The growth temperature is maintained at 400 degrees centigrade, and the temperature difference delta T is maintained at 30 degrees centigrade. For the growth of PbS, that's lead sulfide, the mineralizer is 12m HCl. The growth temperature is 430 degrees centigrade, and the temperature difference delta T is maintained at 20 degrees centigrade. For the growth of TiO2, the mineralizer used is 1.5 mKf. The growth temperature is maintained at 550 degrees centigrade. The temperature difference is maintained at 50 degrees centigrade. For the growth of NiFe2O4, the mineralizer used 0.5 NH4Cl. The growth temperature is maintained at 470 degrees centigrade, whereas the temperature difference delta T is maintained at 12 degrees centigrade. The above lists that I referred to offers examples of alkaline, neutral, and acidic mineralizers. Now we shall talk about advantages of hydrothermal crystallization. Hydrothermal crystallization offers the following advantages. 1. In hydrothermal growth, one usually refers to high temperature of crystallization. However, in reality, this temperature is often rather low as compared to the melting point of the material. It is this relatively low crystallization temperature that makes the technique an attractive means of crystal growth. Number 2, the dislocation density of a hydrothermally grown crystal is less than melt-grown crystals. It is because in hydrothermal synthesis, the crystals grow under less thermal strain, whereas in melt growth, large thermal gradients are present. This is called low temperature, also permits the growth of low temperature polymorphs, which are often unattainable by other means. Number 3, hydrothermal growth uses a closed system. In such a closed system, the atmosphere may be controlled to produce oxidizing or reducing conditions. Number 4, in this technique, one can achieve comparatively rapid rate of growth. Quartz grows as fast as 0.25 inches per day on 0001 plane. This rate of growth is extremely rapid for growth from a solvent-solute system. This large rate of growth is due to the fact that hydrothermal solutions have comparatively low viscosities, together with a large variation of density with temperature at constant average density. This results in rapid convection and very efficient solid transport, permitting large growth rates. Now let us also discuss disadvantages of hydrothermal crystallization. The hydrothermal crystallization, however, suffers from certain disadvantages which may be summarized as follows. Number 1, the need for a well-designed high-pressure vessel with a reliable closure that is capable of withstanding the high pressure generated at operating temperatures. Number 2, the vessel should be structurally strong and also chemically inert, that is corrosion resistant. It is because high purity of the grown crystal is usually of paramount importance, and even a slight autoclave attack is intolerable. Number 3, although hydrothermal growth is relatively rapid, experiments are still lengthy. Number 4, in this technique, there is no provision to observe progress during a run. Number 10, delta F is equal to minus 4 by 3 into pi FL delta R cube plus 4 by 3 into pi FC delta R cube plus 4 pi sigma delta R square, or delta F is equal to 4 by 3 into pi delta R cube into FC minus FL plus 4 pi sigma delta R square. It is given as equation 24.4. As shown in figure 24.1 regarding free energy temperature diagram, it is quite clear that Fc minus Fl is always negative on account of the fact that the liquid is supercooled. Based on equation 24.4, if we draw a graph as shown in figure 24.6, it suggests dependence of change in free energy delta F on crystal formation of radius delta R. It will be as is shown in figure 24.6. From this figure, it becomes clear that delta F is equal to 0 at delta R equal to 0, and delta F is equal to 0 at delta R equal to 3 sigma by FL minus FC. Figure 24.6 shows this free energy of formation of a spherical crystal delta F as a function of radius of the crystal. Slide 12. Now we'll talk about the nucleation rate. Nucleation rate is determined by the number of nuclei formed per cubic centimeter per second. In liquids, there are several groupings of molecules which are transitory and in a state of continuous flux. Such transitory groupings of molecules are technically called as subcritical nuclei with size less than the critical radius R star. Because of free energy fluctuations, these subcritical nuclei form and dissolve because it lowers the free energy, thus making it thermodynamically a favorable process. Application of Boltzmann distribution yields an expression for stationary distribution of subcritical embryos as capital L within brackets R equal to sigma or the summation sign by. Here we shall talk about the experimental setup for liquid phase epitaxial growth, abbreviated as LPE growth. Figure 29.5 A and B shows schematic diagrams of two common reactors that are used for LPE growth. The reactors are classified as either vertical or horizontal. In both the cases, the experimental setup consists of a furnace, solution, and substrate holders. In the growth of 3,5 materials, the setup uses a quartz tube containing a high purity hydrogen atmosphere. For the growth of garnets, the ambient gas is air and only single layers are deposited for bubble memory applications. However, for third 5 compounds, which are required for optoelectronic applications, more than one layer is grown. In the growth of gallium arsenide, tipping method is used, wherein during equilibration, a gallium arsenide substrate is positioned at one end of a graphite board and the solution is positioned at the other end. When equilibration is achieved, the furnace is tipped so that the solution is able to contact the substrate and the process is followed by controlled cooling cycle. On account of limitations of the tipping method, horizontal slider method is used especially for multi-layer fabrication. Both the techniques involving either moving of solutions to the substrate or vice versa are used depending upon the feasibility. There are several invariants of the procedure and technique of liquid phase epitaxial growth. However, amongst these, there is one known as vertical dipping method, which is used mainly for single layers. In this method, the substrate is immersed into the solution for growth. Holder is so designed as to break through any crust on the solution surface, and the provision for scraping off any residual solution after withdrawing the substrate. The experimental setup is shown in a schematic diagram of figure 29.5b. Since the substrate is used in the form of wafer, it is also grouped under horizontal dipping method. The substrate is rotated to give stirring effect, as we do in case of Czochralski systems, which is used in the growth from pure melt. Figure 29.5a is a schematic diagram showing horizontal liquid phase epitaxial growth system for the growth of 3,5 compounds as devised by Deutsch 1975. And figure 29.5b is the schematic diagram showing vertical liquid phase epitaxial growth system used in magnetic garnet growth as devised by Gaze and Geis in 1974. Horizontal dipping is used for the growth of semiconducting crystals. However, there are two difficulties because of which the use of this technique is rather rare. The main problems are as follows. Number one, the first problem is that it is difficult to design substrate holders which provide undistorted flows in semiconductor solutions on account of limited range of compatible materials. Number two, the other problem is that the semiconductor solutions are much less stable in the supercooled state as compared to oxide or halide-based solutions. Because of this problem, spurious nucleation is very much common in semiconductor solutions. The main uses of liquid phase epitaxial growth are the major uses of LPE growth are as follows. Use in growth of layers where purity is of utmost importance as required in the case of semiconducting layers. Number two, use in requirement of growth of those materials where practical alternative techniques are not available, as in the case of magnetic bubble devices. Slide number 13. Now we shall take up dependence of nucleation rate neta on temperature T. From figure 24.6, we know R star equal to 2 sigma upon Fl minus Fc. It is well known that at the melting point, Fc is equal to Fl. So, R star is equal to infinity. It means that at the melting point, the critical radius R star is infinite and F star is infinite and neta is equal to 0. At 0 degree K, the molecules have no kinetic energy and so such molecules cannot move. As such, the critical nucleus is not in a position to gain one more molecule and so neta is equal to 0 again. Nucleation does occur at appreciable rates at some temperatures. So neta versus temperature T curve must therefore have a minimum. If a liquid is cooled so fast past this maximum that no nuclei gets time to form, it becomes a glass. We know that silicate materials are found in amorphous state in nature. The above explanation is an answer to the question as to why silicate materials almost always form glass. For silicate materials, the factor phi given in equation 24.8 is usually extremely small. The merits of silicate materials are highly viscous, with high viscosity and very low diffusion coefficients. These three factors put together makes it very difficult to cool a molten silicate at such a slow rate as to make it possible for nucleation to occur at all, with the result that they almost always form glass and fail to get crystallized. Man has limitations over time, temperature, and pressure. However, nature has no such limitations. In nature, cooling may last for thousands and millions of years, and the process may pass through geological times, which are impossible to happen in the laboratory experiments on growth by a researcher. Thus, opening of the possibility of nucleation and growth becomes impossible for such materials. In contrast to this, phi is very large for water, and as a result, crystallization can be conveniently done, and only the most extreme measures will have to be taken, if at all one is able to do that. Can glass be made? Slide number 14. Now we shall take up heterogeneous nucleation. Let us discuss dependence of growth rate on cooling procedures. Dependence of temperature, T with time, on growth rate for the above said cooling procedures, which includes ramp cooling, step cooling, and pre-cooling, is shown in figure 29.6 A, B, and C. The effect on the growth rate, represented by small v, with time small t, corresponding to each of the cooling procedures, is shown in figure 29.6 A prime, B prime, C prime, respectively. In these diagrams, the time small t is equal to 0 is taken at a time when the substrate is brought into contact with the solution. Now here figure 29.6, A, B, C and A dash, B dash, C dash show variations of temperature T with time small t and their corresponding variations of growth rate represented by small v with time represented by small t for different cooling procedures like A prime, ramp cooling, B prime, step cooling, C prime, pre-cooling. Two types of lines are drawn, A prime, B prime, C prime, which are growth rate diagrams corresponding stirred and unstirred solutions. Full line in these diagrams represent growth rate versus time for stirred solutions, and the dotted lines stand for unstirred solutions. In this figure, the full lines represent growth rate versus time for stirred solutions, whereas the dotted lines stand for unstirred solutions. Let us discuss each of the curves of temperature capital T versus time small t for three cooling procedures and the corresponding curves of growth rate versus time T. Ts represents saturation temperature. For the ramp cooling case as represented by figure AA prime, the growth rate is almost zero, which subsequently rises as the supersaturation increases. But after some time, it decreases. In fact, the concentration capital C can be shown to be related to thermodynamic quantities like enthalpy, capital H, gas constant capital R, and temperature capital T by the relation capital C is equal to C0 exponential of minus H upon RT, given as equation 29.1, where C0 is a constant. If the solution is cooled by delta T, it makes available for precipitation and hence growth an amount which for small delta T is given by delta C of the approximately equal to C0 H delta T upon RT square into exponential of minus H upon RT, which is given here as show equation number 29.2. For a given delta T, delta C will decrease as capital T decreases. There is a possibility of cooling faster as capital T falls to cancel this effect. However, an initial transient will always occur. If cooling is done stepwise, the same initial transient effect will occur, but additionally, with the passage of time, the solution gets exhausted, and for long growth periods, the growth rate decreases. The said solution exhaustion does happen when pre-cooling is done. If the case is that of stirred system presented by full line, in the curve, the initial growth is high, but falls when the solution near to the growth phase gets depleted. It continues for a time, which is given by the expression delta square capital D by D, where delta D represents solute boundary layer thickness and capital D is the diffusion coefficient. As times get longer, the solutions which are stirred supply new nutrient to the boundary layer thickness. This fresh nutrient supplied to the boundary layer thickness is at a rate which attains maximum value at a time of about capital L square upon V. That is the time for the stirring to penetrate the depth capital L of the melt having kinematic viscosity small v. The detailed theory of this process is given in the references cited here and are suggested for any extra information on the subject matter, like Bryce J.C. in 1976 in Crystal Growth and Materials, edited by E. Caldes and H.J. Scheel. Publishers are North Holland, Amsterdam, chapter 11.3. Next is Alwell D. 1976 in Crystal Growth and Materials, edited by E. Caldes and H.J. Scheel, published by Amsterdam, North Holland, chapter 11.6, and Alwell D. Scheel, H.J. in 1975, Crystal Growth from High Temperature Solution, published by the Academic Press, New York. High pressure growth. High pressure growth technique has been applied for the crystallization of diamond. The first confirmed synthesis was reported in 1955 by the General Electric Company in the United States of America. Very high pressure is needed for the synthesis of diamond. Pressure alone is not adequate, since the growth rate has to be kept rapid enough by the use of high temperatures. In actual practice, temperatures used are 2000 degrees centigrade or even more, and pressures above 1 million pounds per square inch. Growth can be extremely rapid, a few seconds being sufficient under some conditions. Davies in 1984 collected a lot of information on diamond, including the processes involved in producing it synthetically. Now let us see what is the apparatus used. The equipment used for such high pressures consists of large hydraulic presses with dies of special high-strength alloys. These concentrate large pressure onto very small volumes, typically less than 1 cubic inch in volume. The natural mineral pyrophyllite is used as a gasket material since it deforms to transmit the high pressure but does not extrude out of the high pressure region. Electric current is passed through the growth region via insulated press plungers for heating the system. A typical reaction chamber arrangement for forming diamond is shown schematically in figure 29.7. Figure 29.7 is a schematic diagram showing reaction chamber arrangement for the synthesis of diamond. We shall now talk about liquid encapsulation zoochronology, abbreviated as LEC growth. When crystals having volatile components are to be grown, a different set of problems come up. LEC is a technique which falls under the category of crystal pulling techniques, which has been developed to overcome one of the main material limitations of crystal pulling, namely that the material to be grown is required to have a relatively low vapor pressure. It is widely used for the growth of 3,5 semiconductor compounds such as gallium arsenide, indium phosphide, and gallium phosphide. Consider growth of gallium arsenide. The solid with the maximum melting point to the tune of 1238 degrees centigrade is in equilibrium with arsenic vapor with a partial pressure of about 1 atmosphere. The arsenic vapor needed is mostly As2. Arsenic vapor at a partial pressure of 1 atmosphere can be provided by an arsenic source maintained at a temperature of 612 degrees centigrade, and the system should not contain any region cooler than the arsenic source. Different types of pulling systems have been used which allow the provision of partial vapor pressure. These include sealed systems with magnetic coupling to have pulling and rotation as required. Systems with liquid seals, for example, boric oxide or close-fitting piston-type seals. However, the only method used on a large scale is liquid encapsulation. It is possible to grow diamonds directly from graphite at temperatures of something of the order of 3300 K and 130 kilobar. A better and practical process involves the use of a solution. Some useful solvents include nickel, where temperature somewhere above 1400 degrees centigrade, cobalt, temperature above 1400 degrees centigrade, and iron, temperature above 1300 degrees centigrade. In almost all these cases, the pressures used are in the range of 54 to 58 kilobar, and the temperature differences between the source and seed say delta T of the order of 10 to 30 degrees centigrade. Nitrogen in small quantities in the form of a nitride is suggested to increase the growth rate. Figure 29.8 is a schematic diagram showing the apparatus used to grow diamond crystals. It is a process which involves the use of metallic solutions. The sodium chloride, that's NaCl, and the pyrophyllite are used as pressure transfer media, and the pyrophyllite seals are used to plug the system. Here, the growth assembly is placed asymmetrically in the heater in order to ensure the temperature difference that's necessary for the growth. In that way, it resembles the temperature differential method of the solution growth, with the difference that very high pressures are required in this case. Figure 29.8 is a schematic diagram of an arrangement for the growth of diamond crystals from metallic solutions. So, students, let us summarize what we have learned in this module. We have learned about the hydrothermal crystallization technique, particularly concerning the growth of quartz. The equal requirements of mineralizers is also explained. The advantages and disadvantages of hydrothermal method are specified. Liquid phase epitaxial growth and the apparatus used for the same are described, particularly for the growth of 3,5 compounds and magnetic garnets. Dependence of growth rate on cooling procedures, including ramp cooling, step cooling, and pre-cooling, is discussed. Reaction chamber arrangement for the synthesis of diamond is described. In general, high pressure growth is discussed.